Okay, welcome to the exciting concluding part of building a uh, various programming constructs in data structure using Jupyter Notebook. So what we're going to do is tackle the very last two missing pieces, which are function declaration and function invocation. And we're going to demonstrate how they could be used with some examples involving recursion. Okay, so let's start with function declaration. Function declaration requires a name, which is a string, and that's going to be the function name. So this name will be used to create a new entry in the context, like the assign construct. It will also have a list of parameter names or argument names. Let's call them parameter names. Which are strings. It will also have a body, which is an arbitrary expression. Okay, so let's do this. We have a class called function declaration, which is expression, and it will have a constructor, which, as I said, would have a name, some parameter names, which are strings of names, are strings given in a list, and then a body, which is an arbitrary expression. It will have, so we're just going to save them the evaluation is actually quite simple in that all we need is to save in the context under the name of the function declaration data structure itself. And there's really nothing that we can return. So we're just going to return none for the evaluation. And the string representation of this will, let's say we have a function with a name, and these are the arguments, and we can specify the body in a curly bracket as such. So we're going to have the name, and the next one is going to be the arguments, but what we'll do is join them using the semicolon, and finally it's the body. Okay, so let's give this a try and see how it's not going to be very exciting because we can't really invoke it, but it gives us a flavor of how things might work. So we can have a adder function that just adds two things. Let's do something like this. Okay, well, how are we going to implement this? Well, we're trying to declare a function, and the function is called add, it will have two parameters, I and j, and then the body is really just the arithmetic operation of looking up the variable I, and we're going to add to variable j. So let's print this out. And we're going to just print out the evaluated result as well, but there's not going to be it's not going to be very interesting because the evaluation will just return null. The action is actually to modify the context. That's what we want to achieve through function declaration. So here's e and e dot evaluate some empty context. So there it is. I forgot the. Okay, so this is the function. It's adding I and j, and then we're going to just do plus ij as an arithmetic operation. Okay. Now the some of you might be wondering, well, how is it that we're able to perform variable reference within the body of the function for the variable name I and j? Like, how is it that we're going to be guaranteed that the symbol bindings for I and j will be available in the context? And this lies in the next one, which is function invocation. So function invocation has quite a number of things. Well, first of all, let's just take a look at how it's constructed. So it's going to be constructed when we invoke a function, we need to specify the name of the function as a string. We need to specify a list of expressions as arguments to the function. And now the evaluation is that for the first time, we need to create a subcontext by copying the existing context and create additional symbol bindings that bind the parameter names to arguments, to the respective arguments. So before we do that, we need to evaluate each argument, and then we bind the results to the parameter bindings, and then we need to evaluate the body of the function. Yep. Okay. And return that. So here's a function invoke. So we need a name, which is going to be a string, and then a list of arguments, which is a list of expressions. Okay, right, very good. Now let's look up the function first. So that's the function declaration that hopefully exists. And what we can do is we need to check that the argument list is exactly the same length as the parameter names of that function declaration. So let's just check that. So if not the length of the parameter names being the same as the argument list, then we really should have a error reported. So here's the incorrect number of arguments. Okay, you can be more specific than that, but anyways. Now the argument values are the individually evaluated results of every expression in the argument list. And then what I need to do is I need to create a subcontext. So let's call it subcontext equals to the context.copy. So first I make a copy of it, and then the subcontext is going to create the additional symbol binding. So I'm going to take a shortcut and just create an auxiliary dictionary of the parameter names to the argument values. So that's the subcontext we do, and the what we return from the function invocation is the body evaluation under the subcontext. Okay. I also want to create a string representation of this. The string representation of this really is the function name with the parameters passed in. So here's going to be the function name, and then the every argument rendered. So it's really the string of every expression for expression in the argument list. Okay, good. All right, well, let's see if we can actually invoke a function. So the first thing is we're going to declare a function, I and j, and here it's just doing the addition, and now we need to call I and j. Okay, so here maybe let's call this function f, just an arbitrary function, and then we call that function. Okay. So the expression is a block that involves a function declaration of f of two arguments, I and j, and then the body is the arithmetic of variable I add to variable j. Now we're able to invoke the function f with two arguments. Let's call this literal. Oops, sorry. I guess we need to pass some arguments. 10, 20. Let's say literal of 10 and literal of 20. Let's just see if that works. Okay, so I have the function declaration here that looks right, and then the function invocation. So at least the construction looks right. Now I'm going to actually evaluate this. I don't really need a context other than the empty one. And there it is. Very good, 30. Now, it may not seem as impressive, but the pieces of programming constructs we have is actually extremely powerful in the sense that it's Turing complete. And what it means is that we're really able to simulate any programming languages that we have been using. So what we're going to do is we're going to try to put together a implementation of Fibonacci numbers. Okay. So the code we'll be implementing is we're going to define the Fibonacci number of n, and we'll say if n is less or equal to 2, then we return 1. Otherwise, it will be we return the Fibonacci of n minus 1 plus Fibonacci of n minus 2. Now you have to be a bit careful that this is a Turing, this is a exponential space and exponential time complexity implementation, but that's all right. This is what the computer programmer has expressed their intent as, and we want to faithfully follow all that. Okay, so how we're going to do this? Well, our program is going to be, and then, okay, of course, once we declare that, I really just want to also be able to have, say, well, let's have a Fibonacci number of 10. Let's see what that is. Okay, the 10th Fibonacci number. All right, well, let's see what the program is going to be. The program is just a single expression of a bunch of things. It's a function declaration of fib, and it only has one argument, n, and the body of the argument, let me just sort it out. The body of the argument is a if else, and we know that for if and else to be constructed, we need a condition. The condition is the variable n checked against less or equal to the literal of 2. And if that is the case, then we return just 1. Otherwise, the Fibonacci number is the arithmetic of the function invocation of fib with one argument, which is the arithmetic of the variable n, subtract literal of 1. Okay, so that's the first one. And this is going to be added to another function invocation that looks almost similar or almost the same, but we subtract 2 instead. Okay, so that's the good. So that's the if and else, and this is a function declaration. So that's the function declaration. And now we need to, so we did all this. Now we need to implement the last, just the invocation. So we're going to invoke Fibonacci number with a single argument of literal of 10. All right. See how this works. Okay. Let's double check this. It's a function. So first we're declaring a function of Fibonacci number. We're saying if it's less than 2, then return 1. Otherwise, return the sum of the Fibonacci number of n minus 1 with Fibonacci number of n minus 2. And it's a bit of a brain teaser to figure out how in the world this would work given all the data structures that we have implemented. I highly encourage you to do that, as you're expected to be able to figure it out. And it has to do with the various entries of the context and this recursive evaluation function. So now we're going to evaluate this. Oops. Okay, so here's some problem. Oh, typed it wrong. The if, oh, there's a typo in the if and else. So let's go back. Ah, that's the typo. Evaluate. Maybe we should just try it out. So let's great. There. Okay, not bigger. So now we tried both if and else. All right. Aha! Very good. So it says that the 10th Fibonacci number is 55. That seems about right to me. Can we do like a bigger one, like 20? And it's 6,765. Now I do remember this one because this is the result you need to obtain for your lab 8. Okay, so your lab will be doing all this in Java. And so this concludes the exercise that of implementing a interpreter backend in Python in Jupyter Notebook.